Okay, I'm back, and in the previous segment, we were talking about how light is both a particle and a wave, and now in this segment, we want to talk about how does the brightness of an object change depending on distance. Well, there's actually two types of brightness. So you got the actual brightness of an object, which is going to be called its luminosity, and is going to be measured in the metric unit watts. So capital W for watts. So like for example, if you go to Walmart, that's a plug for Walmart. So you go to Walmart and you buy a light bulb. And let's say that that light bulb is a 60 watt light bulb. Well, that's a 60 watt light bulb whether you hold it right in front of your eye or if you hold it a mile away. So the luminosity of a star or the luminosity of a light bulb does not change. So it's the same star, it's the same light bulb no matter where you put it. But you also have apparent brightness. So another name for the apparent brightness is called the energy flux. And so that's why it's abbreviated with an F. So the abbreviation for actual brightness or luminosity is an L, and then the abbreviation for apparent brightness or the energy flux is F. So I won't use the word energy flux anymore. So I will just basically either say luminosity or apparent brightness. So those are the kinds of words that I like to use. And the apparent brightness does change because you can take that 60 watt light bulb and you hold it in front of your face and you'd say, boy, that's a bright light bulb. But if you take that 60 watt light bulb and you move it a mile away, you'd say, boy, that's a very dim light bulb. So the apparent brightness does change. So what we want to know is how. So how does the apparent brightness of a light bulb change as you move it away from you? So that's going to be the letter R. So R is going to be distance that you move it away from you. So you can conduct this little experiment at home with a flashlight. So that if you take a flashlight, say this is my flashlight, and you're going to hold it up against the wall and shine the light on the wall, you're going to see that it's going to make a circle of light. So notice the size of the circle of light and also notice the brightness of the light. All right, then start to back it away. So back your flashlight away from the wall and look at how the circle gets bigger, but the bigger it gets, you'll notice it's not as bright as it was when it was up against the wall. So two things are changing. The size of the circle, or we could say the area of the circle, and then also the brightness of it is changing. So in this picture here that you see in the notes, you've got a light bulb, and then at a certain distance, let's call it R sub 1, you see that the light from the light bulb is going through that one square. Now, if we go 2 times further away, okay, so now we're going to go 2 times further away from the light bulb, do you see that in order to catch all of the light that went through that original square, so you got this original square here, and here's the light bulb, and it's sending out light rays like this. So if you want to catch all of this light, you're going to need to have 4 squares out here in order to, well, there's my 4 squares. I had to kind of exaggerate in order to do it. But now it's catching all of that light. And then if you go 3 times further away, you notice you need to have 9 squares in order to be able to capture all of that light. But do you notice that the light is getting dimmer? That's because the energy that was spread out over 1 square is being spread out over 4 squares, and then it's being spread out over 9 squares. So that's the reason why it's getting dimmer, is the energy is being spread out over a larger area. Well, what do we mean by area? Well, this would be length times width. But actually what's happening is the light that's coming from that light bulb is going in a sphere, and then that sphere gets bigger and bigger and bigger the further away from the light bulb it gets. So it turns out that the area of a sphere, the surface area of a sphere, is 4 pi r squared. So that's the reason why you're taking the original brightness of the light bulb, that's the L, so that's the energy per unit time that's coming out of it, and then you're dividing it by the area that it has to go through. Now, I'm not so much interested in the 4 pi part. So what I'm interested in is that the brightness of a light bulb gets weaker as 1 over r squared. Does that sound familiar? Was there anything else that we've learned, as in last lesson, that got weaker as 1 over r squared? And that was gravity. So do you remember big G m1 m2 divided by r squared? Remember that formula? So that the further away you got, the weaker gravity got. Well, the further away from light you get, the weaker the light becomes. So here's the kind of question that I think that you should be able to answer on an exam. So if a light bulb gets 8 times further away from you, what happens to its luminosity and what happens to its apparent brightness? Well, first, the luminosity, it doesn't change. It's the same light bulb. So that part's easy. So the next thing is, how does the apparent brightness change? Well, we said it varies as 1 over r squared. So you need to take the r, which is 8, and you need to square it. So that would be 64. So you could say that the light bulb gets 64 times dimmer, or you could say that the brightness is 1/64th of what it used to be. So either of those two answers would be okay. In our next segment, we're going to talk about temperature. So I'll see you then.